Okay, I think last time we looked at conservative forces. Conservative forces, and we showed that the work energy theorems. So we showed that in the presence of conservative forces, the work energy theorem could be modified, could be written as EB minus EA is going to be equal to the work done by the non-conservative forces. As I go from A to B, non-conservative forces, and if the F vector non-conservative is completely equal to 0 and there are only conservative forces present, then we find that EB minus EA is equal to 0, and that means that EB is equal to EA. So what it means is that conservative forces conserve the total mechanical energy. Careful. So conservative forces conserve the total mechanical energy. This is the total mechanical energy. And we define the total mechanical energy as the kinetic energy plus the potential energy. And the potential energy is given in terms of the conservative force as minus of the gradient of U. Okay, so therefore we can say that U can be written as minus integral F conservative dotted with dr vector, where the upper limit is r vector and this is in general a function of r vector. Okay, so this is what we know about conservative forces. Now we are interested in a particular type of conservative forces called central forces. And I think I've given you the definition for the central forces. Okay, and the central forces are given by F vector of r vector is some function which only depends upon the magnitude of the radial distance and acts in a direction along the radial vector. So supposing this is the source of the force, and let us say I'm interested in some point P over here, okay, where this is what I'm going to call as the field point and this is what I'm going to call as the source point, then the vector that joins the source point to the field point is the radial vector, and there is a unit vector along that direction. So we find that the force depends upon the magnitude of the vector S to P, and it is along the line that joins S and P. Okay, that's what we mean by a central force. Now we can see that I think we have also shown earlier that central forces are conservative. Okay, central forces are conservative, and the potential associated with the central force is given in terms of this function f of r is equal to minus du by dr, where you'll find that u is also a function only of the radial distance and does not have anything to do with the directions. Is that okay? So this is the potential due to the central force. There is another property that central forces have. Let's try to find out that property by first trying to calculate the torque due to the central force. So let us take a look at the torque due to the central force. Okay, so what is the torque due to the central force? That can be given by r vector cross f vector of r vector. So that is equal to r vector cross, this is given by f of r hat. Now since r vector and r hat point in the same direction, this should be equal to 0. But then I know that the torque is given by dl vector by dt. So what it means is that dl vector by dt of a particle that's traveling in the central force has to be 0, which means that L vector is conserved. Okay, so therefore we find that central forces conserve both energy, and by energy I mean the total mechanical energy, the energy and the angular momentum. Is that okay? So now let's see what happens when the angular momentum is conserved. So it means that the particle has to travel in a plane. Supposing this is going to be my L vector, and I'm going to choose my coordinate system such that my z axis points along the angular momentum vector, then the particle must have a trajectory that has to be along a plane that is perpendicular to the angular momentum vector. So I'm going to say that the trajectory of a particle traveling under the influence of a central force must be a plane curve. What do we mean by a plane curve? A plane curve is something which if I put on the table, every point of the curve is in contact with the surface of the table. If I take a stiff wire and bend it every which way and put it on the table, then what happens? Some portions will go above the table, some portions will come and touch the table, and so on. So such a curve will be called as the space curve. Here on the other hand, the trajectory of a particle which is moving entirely under the influence of a central force is going to be a plane curve. And this plane here is perpendicular to L vector. Okay, so these are the key features of this. Now, if the trajectory is entirely inside a plane, then I can use circular polar coordinates to describe the location of points on this plane. Is that right? So let us see what would those things be. So if I take a particular point over here, the distance will be rho and the angle here will be theta. So my coordinates are rho and theta in the xy plane. So this is my x and this is my y. Is that okay? Why don't you put your bag down? You'll be a little more comfortable. Exactly. Nobody is going to run away with it. Okay? Yeah. So then I can have rho comma theta, and if I'm interested in the three-dimensional vector for this can be written as r vector, which is characterized by rho comma theta comma z is equal to 0, right? Because z equals 0 defines the xy plane. So we can also have unit vectors rho cap, which we have already dealt with before, and there is going to be a theta cap. So I'm going to get rho cap, which can be written as cos theta I cap plus sin theta j cap, and theta cap is equal to minus sin theta I cap plus cos theta j cap. And we find that these unit vectors are not constant, they can be differentiated. So rho cap dot, where dot means derivative with respect to time, so that can be written as minus sin theta I cap plus cos theta j cap times I have to multiply by d theta by dt. So this can be written as, and you can see that this is nothing but just theta cap and I have a theta dot. Okay, so likewise theta dot, and you can see likewise that theta cap dot is going to be equal to minus of rho cap times theta dot. Is that right? So we are going to be needing these relations as we go further. So let us try to find out what is the angular momentum of the system. The angular momentum of the system, so here is my particle which has a mass m, and the axis is going to be through the origin. So what is so L can be written as I times omega, where I is the moment of inertia and I is given by m into rho squared, okay, and omega is nothing but just equal to theta dot, right, d theta by dt. So therefore I am going to find that L is equal to m rho squared theta dot, but I am told that this is equal to a constant. So therefore I am going to find that rho squared theta dot is going to be equal to L by m, and that is equal to a constant. Now rho squared theta dot has a very interesting interpretation. We can see what happens. Supposing here is my trajectory, and let us say here is the position of the particle at time t, and let us say here is the position of the particle at time t plus dt, and let us say this fellow is d rho, and this angle is d theta, and this distance is rho, let us say. Okay, can we find out what is the area of the triangle? Okay, so the area of the triangle I am going to call as delta A, and delta A, you can see that since there is a very small change, dt is very small, so this can be regarded as a right angle triangle, right? So it's going to be half base into height, so that I can regard the base as rho and the height as d rho. So that's going to be equal to 1/2 rho d rho. But then I know that d rho can be written as rho times delta theta, right? So therefore I'm going to get delta A is equal to 1/2 rho times d rho is rho times delta theta, that is 1/2 rho squared delta theta. Let us divide both sides by delta t. So I am going to find that delta A divided by delta t is going to be equal to 1/2 rho squared delta theta by delta t, and that is 1/2 rho squared theta dot. Now delta A by delta t is called the aerial velocity. And we find that the aerial velocity is related to 1/2 rho squared theta dot, which we have identified as equal to L by m. So the aerial velocity is equal to L divided by twice. Okay. Now Kepler, when he was studying planetary motion, stated that the radius vector of the planet sweeps equal areas in equal times, right? So sweeping of equal areas and equal times means aerial velocity is a constant. Okay? Yes, exactly. And that automatically means that L by 2m is a constant, which means that angular momentum is conserved. Okay? So therefore this Kepler's second law which essentially means that dA by dt is equal to constant, also implies that L vector is conserved. Now while Kepler discussed this in the context of the gravitational force, because it was assumed that the planet was held to the sun by a gravitational force. But what we have proved is something more general than that. What we have proved is that both Kepler's second law and conservation of angular momentum are valid for any central force. It just so happens that the gravitational force is also a central force. Okay. So how do we write down a central force? I just pointed out again, F vector of R vector is F of R times R hat. Now sometimes you can see a rather complicated form of this. Supposing the source is here, and let us say the field point is there, but neither is at the origin. Let us suppose the origin is somewhere else. So this is the origin. So this is my RS vector, this is my R field vector, and let me define a vector here called R. So then what does this vector R do? Well, I know that this is given by R field vector minus R source vector. So how would I write down the expression for the central force exerted by the source at this point P? So I can write that F, which will now be a function of, let us say, the field vector, okay, and that can be written as F of R, which is modulus of R field vector minus R source vector, times R cap, which is defined as R field vector minus R source vector divided by modulus of R field vector minus R source vector. So you see, this looks quite complicated, but it carries the same meaning as this does. Okay, both of these are expressions for a central force. So you should not be scared of the complicated looking form. F of, say that again. Yes. So I would say that the modulus of R is equal to modulus of RF vector minus RS vector. Right? I am expressing R vector in terms of the source and the field point coordinates. Excuse me? Oh, this one. Well, usually what happens is that the source is stationary, right? And the object that is experiencing the force is moving about. So I would like to describe this at the location of the field point. So I am referring to this as, so the argument I am going to put is simply the radius vector of the field point. But it's true, it also depends upon the location of the source point. But that is considered a fixed thing in the problem. Okay. All right. So so that's what I have. Central forces that are? Yeah, sure. Supposing I'm going to have a point, over here, and let us say I attach a spring, so that the spring can move about in any 360 degrees direction in any plane, right? So then obviously the force it's going to exert is going to be attractive. It's going to be along the line that joins it, and it's only going to depend upon the distance. So the force exerted by the spring is going to be central. Okay, that's one example. All right, any other question? Okay, so we have this. Okay. All right, so that's what we have for the central force. Now let us try to also look at how to write down the expression for the motion of the particle in the central force. Okay. How do we do that? You know that F vector of R vector, I'm going to go to this formulation because it is simpler. F vector of R vector is equal to m into the acceleration vector. This is my Newton's second law. So let us apply the Newton's second law for a particle moving in a central force. Okay. So what we do then? We know that this is equal to F of R times R hat, that's equal to m into, what do I get here? This can be written as d of v vector by dt. Is that right? So now let us take a look at it over here. We got rho vector is equal to rho times rho cap, and therefore I'm going to get d rho vector by dt is equal to v vector, and that's equal to rho dot times rho cap plus, what do I get? Rho times rho cap dot. So that's going to be equal to rho dot rho cap plus rho times, I'm going to get theta dot theta cap. Now if I differentiate this again, and I have done that, a vector is equal to v vector dot, and I'm simply going to write down the results. It is rho double dot, okay, minus rho times theta dot squared rho cap, okay, plus I'm going to get twice rho dot theta dot plus rho times theta double dot times theta cap. That is the expression for the acceleration in circular polar coordinates. We have done that where? Perhaps in the second or third lecture. Okay, so it's been done before. So let me substitute that. So I'm going to get f of rho, and I think I should be using rho everywhere and not r. Okay, so I can have f of rho cap. So f of rho cap is going to be equal to m into rho double dot minus rho theta dot squared rho cap plus m times twice rho dot theta dot plus rho times theta double dot times theta cap. So you can see that the left hand side only has a rho cap term and does not have a theta cap term. So therefore this theta cap dependent term must vanish. Okay, and f of rho must be equal to the coefficient of rho cap. So let's try to do that. So equating coefficients of rho cap and theta cap, what does that give you? That gives you two equations. One is of course f of rho is equal to m into rho double dot minus rho times theta dot squared, and then I'm further going to get m into, this is one equation, the other equation is m into twice rho dot theta dot plus rho theta double dot is equal to 0. Right? So you can see that this equation contains a theta and that equation contains a rho. So these equations are coupled. These are coupled equations. Okay, how do I uncouple them? Well, I uncouple them by actually solving one of them. It turns out that I can solve them because the solution is simple. Okay, if it wasn't, then I would have to worry about what to do. So let us take a look at the second equation, which says that m times, I'm going to get twice rho dot theta dot plus rho times theta double dot is equal to 0. That's the equation. Multiply both sides by rho. Then what do I get? M remains as it is. I don't want to throw it away yet. So I'm going to get twice rho times rho dot times theta dot plus, I'm multiplying by rho, so this becomes rho squared, and this can be written as theta double dot. Okay, and 0 equals. So that can be written as m times, I can write the first term as d by dt of rho squared, and I'm going to get a theta dot plus, I can write rho squared times d by dt of theta dot. So if I look at the terms of the rectangular bracket, I'm going to have derivative of the first function times the second function plus first function times the derivative of the second function. So what is this? This is the derivative of the product of these two functions. So I can therefore write m times d by dt of rho squared theta dot is equal to 0. Now since m is a constant, I can bung it inside the derivative term. I can write d by dt of m rho squared theta dot is equal to 0. But I know what m rho squared theta dot is. What is it? Angular momentum. So this is nothing but just equal to dl by dt. Or I can say dlz by dt, and that is equal to 0. Is that right? So therefore I must have m rho squared theta dot should be equal to lz. Or I'm just going to call it as L. Okay. So once I do that, I can solve for theta dot. Theta dot is equal to L by m rho squared. And then what is going to be my theta dot squared? That's L squared by m squared times rho raised to the power 4. Let us substitute this into the radial equation. If I substitute this into the radial equation, what do I get? I'm going to, so this is my radial equation. I'm going to find that f of rho is going to be equal to m, and this rho double dot can be written as d times v rho by dt. Is that right? And then the next term becomes plus, no, there is a minus sign, my apologies. So I'm going to get a minus sign, and I'm going to get a rho times, I'm going to get L squared by m squared rho raised to the power 4, and there is an m here too. My apologies. So there is an m here and there is a rho there. Is that okay? So there are some cancellations here. So this m cancels with the squared, and this rho cancels with the 4 to give me a 3. So what do I get? So this becomes equal to m into dv rho by dt minus, I'm going to get L squared by m times rho cubed. Okay. Now I can write dv rho by dt as equal to dv rho by d rho times d rho by dt. So that is equal to v rho times dv rho by d rho. Feeling too sleepy? No. Okay. So this can be written as the derivative of d by d rho of v rho squared. But that's going to pull out a factor of 2. So to correct it, I'll put a half. Okay. So let us see then what is my term. So I'm going to write, so I'm going to find that f of rho can be written as mass times, there is a half times a d by d rho of v rho squared minus, I can have an L squared by m. Okay. And what do I do with L squared? What do I do with 1 by rho cubed? Well, I can put a plus sign here and take a d by d rho of 1 by twice rho squared. Right? Let's do an aside and verify this. So let's try to calculate d by d rho of 1 by twice rho squared. So that is going to be equal to, the half remains there, and this becomes a minus 2 by rho cubed. So this 2 cancels with the 2, and I'm going to get a minus 1 by rho cubed. And that's exactly what I want. I want a minus 1 by rho cubed. Is that right? So now let's try to simplify this further. I can write this as d by d rho of 1/2 m times v rho squared. Okay, and then I'm going to get a plus d by d rho of, what do I get here? L squared by twice m into rho squared. And that is equal to f of rho. F of rho can be written as minus du by d rho. Right? Because f of rho is associated with a potential u. So you can see that all these three terms contain a d by d rho. So let us collect all the three terms together. So what do I get? I'm going to find that d by d rho of 1/2 m v rho squared plus L squared by twice m rho squared, and I take this fellow onto the other side, I'm going to get a u, and that should be equal to a 0. Is that okay? So now, so if the derivative of something is 0, that something must be a constant. Okay, that something must be a constant. So therefore I should have 1/2 m v rho squared plus I'll put a u, there is a plus sign here. There is a plus u plus L squared by twice m rho squared is equal to a constant, and let's call that constant as the total energy E. Okay, so therefore I'm going to get this equation, which is that 1/2 m times v rho squared is equal to E minus these two terms u plus L squared by twice m rho squared. So this term in the rectangular brackets here is sometimes called the u effective, which will also be a function of rho. Is that okay? So this is called the effective potential. Okay, there are two terms in the effective potential. What are those two terms? One is, of course, the potential due to the force. Okay, and the other one, which is the second term, it is called the centrifugal force or the centrifugal potential. Right? You must have all heard of the centrifugal force. This is like the potential associated with the centrifugal force. Right? The centrifugal force is also central, which is why it can be characterized by a potential. Okay, so these two together define the effective potential. Okay. So now this tells us something very interesting here. It tells us, for instance, that 1/2 m v rho squared has to be positive or 0. It cannot be negative, because otherwise v rho squared would have to become imaginary. So therefore this has to be positive. So if I have some graph, let us say, which is something that looks like this, where let us say this is my rho axis, and I have let us say a certain energy. Okay, then what does this tell us? If I am present somewhere in this region, for instance, what would happen? I would find that my energy is less than the potential energy. So this E is less than that, so that means this would have to become negative. But I've just told you that it cannot become negative. So the regions in which this effective potential graph rises above the energy line is a classically forbidden region. What it means is that is a classically forbidden region. What it means is that you cannot find a classical particle in this region. It will never exist there. Okay? But you might wonder why we call it classical. Why do we do that? What is your guess? Yes, so quantum particles behave very strangely. So to distinguish that behavior, we use the term classical over here. Is that okay? How much time do I have? Okay, I have to rush through some things. So let me do one thing. Let me describe the general solution to a central force problem. Okay, how would I do that? Well, first of all, let us take a look at this equation. 1/2 m v rho squared is equal to E minus U effective of rho. Is that right? So that means I'm going to be able to write v rho squared is equal to 2 by m into E minus U effective of rho. Okay, and therefore I'm going to get V rho, which is d rho by dt, can be written as, I have to take the square root, so there is a 2 by m square root times an E minus U effective of rho raised to the power half. Okay, so now I can integrate, so I'm going to find that d rho divided by square root of 2 by m times E minus U effective of rho raised to the power half is going to be equal to dt. So let me integrate and we'll put the initial conditions in the limits. So let us say that the time goes from some t0 to t. Okay, and the corresponding limits for rho are, let us say, rho 0 to rho. Okay, so therefore I'm going to find that integral d rho divided by square root of 2 by m into E minus U effective raised to the power half, okay, is going to be equal to t minus t naught. So what exactly does this equation do? It gives you the time as a function of rho and the initial conditions rho naught and t naught. Not a very useful thing for us. We have to invert this equation. Invert this equation to find rho as a function of t, comma rho naught, comma t naught. This is what we really want. We want to know how does the radius vector change as a function of time. But in order to do that, we have to carry out this integral and then we have to invert the function represented by that integral. So the solution is not immediately obvious. There are certain steps that you have to go through, right? But these are all supposedly doable in principle situations. Okay? All right, that tells us how the rho behaves as a function of time, okay, through this process. What about the angle? How does the angle behave as a function of time? Well, we do know that my apologies, that rho squared theta dot is equal to L by m. Is that correct? Now L and m are constant, so we know this. So therefore I'm going to find that theta dot is equal to d theta by dt is going to be equal to L by m into rho squared. Now let us suppose I've carried out all this process and now I know rho as a function of time, let us say. So this is equal to L by m. I'll put that aside and I get a 1 by rho squared, which is a function of time now. Okay, but then I'm going to have a d theta by dt here. So this is equal to d theta by dt. So I multiply by dt, so I'm going to find that d theta is equal to L by m times dt divided by rho squared of t. Okay, so this is what we get. And now we integrate again. So I'm going to find integral d theta and integral this, and I have to put the appropriate limits. What are those limits? I go from t0 to t and I go from theta 0 to theta. So therefore I'm going to find that theta minus theta 0 is equal to L by m, and then what do I get? Integral from t0 to t dt divided by rho squared of t. Okay, so again, what does this equation do? This equation tells us what we really want to know, that is theta is a function of t comma theta 0. That's what we really want. Okay, so now I have got these three equations. Let me call them as one, so two equations. So I'm going to have this as equation 1. Let me call this as equation 2, But sometimes we may be interested only in the trajectory. We are not interested in what happens as time goes on. We just want to know what is the trajectory. So that means I have to eliminate the time between equations 1 and 2. How do I do that? Well, let's go back to this equation here. What is that? We'll go back to our equation for d theta by dt. And d theta by dt is going to be equal to L by m and 1 by rho squared of t. Is that right? And now let us take a look at this equation over here. Okay, and what does that tell us? That tells us that I can write this as dt is equal to d rho divided by square root of 2 by m times e minus u effective of rho raised to the power half. Substitute for dt over here. Then what do I get? I am going to find that d theta, okay, or rather let me multiply this by dt. So I am going to get d theta is L by m times dt divided by rho squared of t. So I am going to find that d theta is equal to L by m 1 by rho squared of t, and substitute for dt, which gives me a d rho divided by square root of 2 by m into e minus u effective of rho raised to the power half. Is that okay? Integrate both sides. So I am going to get, so there is an integral here and there is an integral here. Mind you, rho squared has to be included in this integral. So I am going to be left with theta minus theta naught is equal to, there is an L by m, and I can take this fellow outside. I think I'm going to get a square root of m by 2, and then I'm going to get integral d rho going from rho 0 to rho divided by, what do I get here? I'm going to get a rho square times e minus u effective of rho raised to the power half. There we go. So again, this is a very inconvenient equation. What does it do? It gives you theta as a function of rho in terms of rho naught and theta naught. Wake him up. Okay. What I would really like to know is the inverse of this function. So I'd like to know rho as a function of theta comma rho naught comma theta naught. So again I have to carry out an inversion. So if I'm able to do all of these things, then I would have completely solved the problem of a central force, regardless of what that force is. So these equations encapsulate the complete total solution of the central force problem for any arbitrary central force. We shall now examine this situation. Okay, we shall now examine this situation for the case where the central force happens to be the gravitational force. Okay, so for the gravitational force, what we find? We find that the force F vector of R vector is given by minus gm times m divided by r square times r cap. So that means if I have a star over here and a planet over here, so this is my star and this is the planet, okay, and there is going to be a radius vector for the planet, and this is going to be my r cap. Okay, so what's going to happen? The force is proportional to the distance inverse square, and it acts along the direction of the radius vector. Now I'm going to put a minus sign here because it is attracting. Supposing I were looking at a Coulomb force, where I had a positive charge and another positive charge. So that force would be repulsive. So it would be a central force, but a repulsive central force, and not an attractive central force. Is that right? So that's what we get. And so this can clearly be written as F of R hat. And we can see that F of R in this case is minus GMM divided by R squared. So instead of writing out all these factors G, M and M, let me just call this as minus K by R, where K is a constant. What is G, by the way? That is the gravitational constant. R squared. Thank you. Okay. So what is its value in MKS units? It is of the order of 10 to the power minus 11. Very small. Okay. Yeah. So it is one of the weakest forces of nature. Okay. So what is the potential associated with this? So we know that this should be equal to minus du by dr. So therefore I must have du by dr must be equal to k by r squared. So therefore I must have u of r is going to be equal to k times integral dr by r squared, and that's minus k by r. Is that right? So that is the potential. So now let's try to go and see what happens to this equation. 1/2 m v rho squared is going to be equal to, this is equal to the energy minus the U effective. What is U effective? U effective is equal to U of R, that is minus K by R, okay, plus the centrifugal potential, which is L squared by twice m times r squared. Is that right? So let us try to plot the effective potential for the gravitational field. Okay. So if I now take a look at this term is negative here, right? So let me draw this. So what happens at r equal to 0, this has to be minus infinity. And it has to lie below this plane. So this is the zero energy. So this is the energy axis. Okay. So therefore this has to come from minus infinity, and it will go to 0, because as r goes to infinity, right, this term will go to 0. But it goes to 0 somewhat slowly because there is only 1 by r. What about this term? This term, mind you, is positive, right? And it has a 1 by r squared. Can you tell me what happens to this term as r goes to 0? Positive infinity, but it's a greater than this negative infinity because it has a 1 by r squared. So therefore this is going to be like this. But it's going to fall off much faster than this fellow, because there is a 1 by r squared as r goes to infinity. Now what I'm looking at is the sum of these two graphs, right? So very close to the origin, this is the origin, I'm going to have a large positive number, and then it's going to dip because eventually this is going to take over. It's going to dip, okay, and then it's going to rise again a little bit, and then it's going to go to 0. So I'm going to get a well over here, but it starts from a very large positive value and goes to 0. But it never crosses the 0 line, right? That is very important. Okay. So now I can look at what happens at various energies. Supposing I choose an energy level, energy value over there. So this energy corresponds to E is greater than 0, right? So there is going to be one intersection. So we know that at points that are lying in this region over here, what's going to happen? At some point over here, the potential energy is going to be larger than the total energy. So kinetic energy will be negative. So this shaded area is the forbidden region. So that means this particle comes all the way up till here and goes back again. Okay, so it is going to come here and it's going to go back, right? So this orbit is supposed to be a hyperbolic orbit. So all orbits for energies greater than 0 are unbounded orbits. They come close and then go back and they never come back again. They are hyperbolic orbits. What about an energy that is exactly along the E is equal to 0 line? Well, they are unbound too, because there is only going to be one route. So each of these points are called the classical turning points, because the particle has to turn, right? Its 0 must change its sign. So it has to go back again. So therefore here what happens is you again have unbound orbits, okay? But these orbits are now called parabolic orbits. Okay? Now what happens if I choose a negative energy for the system? Then there are going to be two turning points, right? So they correspond to different values of radii, R1 and R2. So here it is a bounded orbit, and the origin is at the focus. So this distance is your R1 and this distance is your R2. And R1 plus R2 is the major axis, which is called twice A, where A is called the semi-major axis. So the shape of the orbit is an ellipse. Okay. Now what happens if I lower the energy further down until it is tangent to this curve? Then it's as if both these roots coalesce. That means R1 must be equal to R2. That means the focus moves towards the center and the orbit is a circle. Okay, so this corresponds to the smallest energy possible value, E min. So E is equal to E min. Okay, let me stop there. Thank you very much. We shall next try to calculate the parameters of these orbits by looking at the energy level diagrams. Thank you.